All right, thank you so much, Ted. Again, while I'm getting set up, if anybody has any questions, this would be a great time. Let's see. All right, hearing nothing. So we've talked a lot about the kinds of things that we can do with Neuron. We've talked about doing it for the graphical interface. We've talked about some numerical methods. So let's turn to scripting. And so here, for example, on the left is a complete code, except for the morphology, which I'm loading here. This is basically a save file, a SES file. When we do the save session, can generate a SES file storing all of our, in this case, if we used import 3D, our morphology that we're doing. So if I did that, here is a complete file for simulating the picture and generating the picture that we have right there, where we've got some sort of a action potential spreading around this pyramidal cell. So I'm not going to go through it all right now, but we will get to all of the pieces that we need throughout this discussion. So let's just get into it. So far we've looked at, again, like I said, doing a lot of setup, simulation, even analysis with the GUI. This gives us a sense, we can save session files, and this gives us a sense of permanence. We can actually go back in, if we understand how they're written, we can even go back in sometimes and modify them. We've talked about being able to get output from a cell builder and then use that in Python. We could do actually everything in Python if we prefer to work that way, or beautifully, we can mix and match, and we can do some things in the GUI and some things in Python, and that's often one of the best ways to go about doing this. So what do I mean when I say that we want to script Neuron? So there's nothing to a script. A script is just a file that happens to have computer readable instructions for performing a task. Usually these are also going to be human readable and writable, so like a plain text file. And we can use scripts in Neuron to set up a model that's supposed to say model, define and perform an experimental protocol, record our data, save and load data, and obviously do any kind of analysis that we may want to do. Why would we write a script? Well, if we write a script, that helps us ensure consistency, and it reduces the amount of effort that you have to do. You don't have to click around all the time. It's going to make it easier to compare the suitability of different models, because I can just have both and run both, and maybe I can swap components between. If I have two different things, it's relatively, and I structure them the same way, I can reuse individual pieces. Moreover, it makes it easier to do experiments over and over again, right? If everything's just a script, we have what's known as a for loop. We can maybe run the variations of the parameters to explore maybe the effects of different drug dosages on a model network. You wouldn't want to necessarily have to go back in and manually set everything. Likewise, if we were to change the experimental protocol, we wanted to run our simulation, but you know what? We decided that we needed to apply the drug for a different period of time or stimulate a different group of cells. Then if everything's written as a script, I can just make that little ABA change that I want to do and just rerun it and let the computer deal with it instead of sitting there manually going through my experiment. And the other thing that ties into sort of ModelDB is this also lets us provide a complete reproducible version of the experimental protocol. So if everything's defined in a script, then in theory, at least, you give that script to somebody else and they can go and they can run the same simulations. And so then they can go and build on that and see whatever you saw and look into it, right? Because maybe they want to ask a different question. So how do I learn more about all of the scripts? So if you go to the Read the Docs page on the left under the section called Neuron Scripting, there is this link for Neuron Python documentation. We've already seen that earlier, but that's where you can go, for example. So here, if you were looking at range var plot, which is what in the graphical user interface is called a space plot, where you want to draw the concentration or membrane potential along some path between 2 points in a cell. And you know that it's a range bar plot. Here's the API documentation. You can go, you can read all about it and see what you need to do if you want to plot it in either Neuron's traditional interviews graphics or using Matplotlib, Plotly, ggplot, whatever it is that you like to use in Python. I will also point out that since, as has been mentioned, Neuron does support more than one programming language. And again, much like with combining with the GUI, you can mix and match programming languages as well. So there is on the top right of every page in the programmer's reference, you can actually switch to between programming languages. So you can go between Python and Oak. The other thing that I will point out here also, if you should find something and you say, hey, you know what, this needs an example and I can make it, or this has a typo or anything like that. If you ever run anything that you wish were better on the documentation, well, you can help. On the top right of every page in the documentation, we have this edit on GitHub link. If you go there, you can make a fork and then make a pull request of the page. All of these pages are available in GitHub. You can go, you can make the modification, make the pull request, and we can work with you to get it into the documentation and make things better for everybody. So thank you in advance for that. All right. So how do we actually get going? If we want to run stuff locally, we're going to need a version of Python. The good news is if you have a Mac or you have Linux, you probably already have Python. You can try by just opening up a terminal and typing Python and seeing what happens. If it's happy with you, then congratulations, you have Python. If not, really, Neuron's perfectly happy using basically any Python distribution. You can get Python from sort of stock Python, which is from python.org, or there are various providers of Python Plus. So Python plus a number of other modules and other scientific libraries that might be useful. So many people, for example, use Anaconda, and you can go to anaconda.com/product/distribution to go and get their installers. And then you can go and run that, and then you'd have Python. We could also, of course, do this on the cloud. Once you have Python, how do you actually run it? Well, there's two main options for how to use Python to script Neuron. What I usually do is I write my code in a programmer's text editor. So something like Visual Studio Code. So here I'm showing a screenshot of Visual Studio Code. It's free. It's available for all platforms. And importantly, it's got syntax highlighting for all the languages that Neuron supports. So that's Oak, that's Python, that's InModal. You have to enable an extension, but the first time you open a mod file or a Oak file, it will tell you, hey, look, I know what to do about these files. Would you like to enable an extension? You say, yes, that sounds wonderful. The extension that you're looking for is VS Code-Neuron in Visual Studio Code. There's something similar for Sublime, for example. And so, hey, look, here's your mod file with keywords highlighted. So parameter, units, initial, derivative, and so forth. And likewise, if you were to look at a Hoke file or a session file, it would do the right thing as well. Yeah, so here, for example, is the full code. Again, it runs and generates an action potential in response to a current clamp injection. And again, we'll talk through all the pieces going into that. And then once you have this Python file, you can just run it by typing Python. What? Well, that's weird. But so you would, oh, there you go. You can run it by typing Python and then spike demo, let's say, because I saved this as spike demo. So it's Python spike demo, and there it is. It'll pop up, in this case, a matplotlib window, and it'll show you the action potential. Why is it doing that? Because I told it to. You know, and I'm using matplotlib for graphics, but there are many, many Python graphics libraries, and obviously Neuron's graphics libraries are always available to you as well. The main alternative to that is to use what's known as a Jupyter notebook. You can do this either locally, just Google it, and it'll look something like this on the left, or there are various cloud providers. So Google Colab is as on the right, so you can just run Neuron inside of Google Colab. If you have any late night desires to do some Neuron simulations on your phone, that's a great way to do it. It's also supported by open source brain. If you would like to run your simulations on open source brain, Neuron's already installed and everything's just there. The one minor limitation, if you're working remotely and doing a cloud-based environment, be it Colab or open source brain, you won't have access to Neuron's interviews-based graphics. And so you would have to use Python things instead. Does anybody have any questions about getting started with Neuron and Python? So if not, can I get a show of hands here? How many people have used Python before? How many people, let me restate that. How many people are comfortable with Python? Okay, so not many. So let's go through a brief introduction then to Python. There is a link, tinyurl.com/whatever I said. But here's what we'll do. I'll just take this link and I will paste this into the chat here. So if you would like to follow along on Google Colab, so I'm just going to use Google Colab, you can go ahead and hit File. So open that link that's in the chat and hit File. If you save a copy in Drive, and then you can open a new tab apparently. And then there you go. So you have your own local copy and you can follow along and do experiments. And I wonder if something was different, how would it be? Well, let's just find out. All right. So how do we Python? If we're using a Jupyter environment like this, basically we have a whole bunch of cells. You see that this block of things is highlighted. I could click down here and it highlights the next block. I could click here and it highlights the next block. Each one of these is called a cell. Doesn't really matter. But the point is to advance from one cell to the next and run the simulation or run whatever's in there. I'll just hit Shift Enter. So this is a text box. I can hit Shift Enter and I'll run it and it does nothing. I'll hit Shift Enter and I'll run it and it does nothing. But here's the thing. So before we do any simulations, before we do any analysis in the computer, we need to have a way of getting a result back from the computer. And one of the easiest ways of getting a result back, graphs are great and we want graphs ultimately, but one of the easiest things that we can do is just have a computer display it some text, display a number, do a calculation and tell me what the result was. Because if you can't tell me what the result was, it doesn't matter what you figured out. And so in Python, the way that we do this is the print function. And so we just write print and then parentheses, we put whatever we want to print out. If we wanted to print out some exact text, I'll put it in quotation marks. So I'll hit print, quote, Neuron is a great tool for simulation. And then sure enough, it runs it and it prints that out. And then if you didn't see what happens, you can always click back up there and say, did you see it? You can modify it. You can do that experiment. Hey, so Neuron's a great tool for simulation. Did you see it? Or I guess really, do you like it here? So you can always go and you experiment with this and see how these things go. So we want to print out an exact message. Okay, that's great, but it's not really the result of a calculation. If we want to do calculations, we can use the usual sort of computer math notation. So an asterisk is multiplication, a slash is division. There's some variations as to what counts as raising the power. So in Python, it's 2 asterisks together. So usual order of operations and all of that applies. So print 5 times 3 plus 2 is 25, but 5 to the 9th, 5 times 9 rather, is this 45, right? 3 squared is 9. 5 squared is 25. So 5 times 5 squared is 125, and so forth. And so we can print out individual results whenever we do a calculation. And then so one of the things that we do, if we have, for example, a object in neuron, say the soma, we have something called the soma, and I want to print out its diameter property. There's a little spoilers for what's coming ahead, but the diameter of the soma is soma.diam. And so I could just say print soma.diam, and then it'd print out whatever the diameter of the soma was. Can't do it now because I haven't defined the soma. So next thing that we can do, though, is we can give ourselves variable names. So we don't want to ever repeat ourselves. We don't want to do a calculation more than once. You know, we want to remember what we've done before. And so it's an extremely powerful tool to be able to just give things a name. Even if we're only doing it once, it's sometimes helpful for ourselves when we go back to read anything that we've written to break a big math problem down into small pieces where every piece has a meaningful name. So I could say, for example, diameter is 4. And then, so that's assigning the value of 4 to the variable known as diameter. And then by doing this, I have, anytime that I see diameter going forward, unless I change it, then diameter will behave as 4. So here I've got a print function. It has 2 arguments. I didn't tell you what would happen if it had 2 arguments, but it prints both of them, shockingly enough. So if I say print, the diameter is, comma, diameter, the first part's in quotation marks, so it's the exact string, the diameter is, and then the second part is the variable, but the variable is 4, so it's going to print out 4. And likewise, the square of the diameter is 16. And sure enough, I can run that and get that result. Right, so we've gotten results and we've assigned variables and we can do some calculation. There's a lot there. So once we have all of this, you know, our cells are complicated things. They have many parts that are associated with them. We're going to want to, sorry, I looked at the chat and got distracted. We're going to want to look at, we're going to want to loop, right? We're going to want to do things more than once. It's one of the great things about computers. You can have the same experiment be done multiple times, but with different current injections, or you want to apply the same thing to different pieces. So here, for example, if I have a list of cell parts, lists in Python, by the way, are denoted with these square brackets. So if I have cell parts, and cell parts is a list, so I've got a soma, I've got an apical dendrite, I've got basals, and I've got axon. So I'll just put that in square brackets. So there's a list of length 4. And then I want to do something to each of those things. So I'll do it one at a time, and I'll just sort of loop through. I'll do the first one, and then the second one, and then the third one, and the fourth one. And so for part in cell parts, I have my list. And so the first time through, I'm going to run it 4 times since my list is length 4. The first time through, part is going to be equal to soma. The second time through, it'll be equal to apical, and so forth. So then this is going to print out a pyramidal cell has a soma. A pyramidal cell has a apical. Let's see what happens. So I run it. Sure enough, there it is. There's some white space issues. We'll get to that later. But in any case, this gives you the gist. We can do the same thing over and over again using a for loop. And by the way, please, if you do have questions, do feel free to ask them on the chat as they go along. And also, please feel free to play along and see if you can see how these things go as well. If I want to grab a particular item from a list, I'll use square brackets and then I'll put the position on that list. So if I wanted to print out the item from my list of cell parts, then position 2, well, okay, my list has 4 items in it. You might think it goes first item, second item, third item, fourth item. But in most programming languages, notably not R or MATLAB, In most programming languages, we start actually counting at 0. So it's 0th item, 1st item, 2nd item, or sometimes I like to say 0th item, 1th item, 2th item, 3rd item. So the 2th item is actually the 3rd item in our list. So it's basal. So let's try it. Print cell parts 2, basal. If you're wondering, let's see, well, what's the 0th one? Well, the 0th one is soma. That means the 1th one is apical, and so forth. If I have a list of things, if I have a list of parts of the cell or a list of cells, right? If I'm doing a simulation, I probably am going to have a big network simulation. I'm going to have a list of cells somewhere, not just list of parts of the cells. I want to know if a given thing is in that list. Like, is this, I have a cell, I'm looping over all my cells. Is this cell in my list of excitatory cells? Is this cell in my list of pyramidal cells? Well, is brain in my list of cell parts? Well, certainly not, right? The brain is made of cells. The brain is not a part of a cell. Is the soma, though, in my list of cell parts? And I can run that, and why, yes, it is. And if I wanted to add an item to a list, I do append. So we may grow lists. We might not necessarily hard code them. But so this allows us to do repeated actions, repeated calculations, right? We, again, like I keep coming back to this parameter sweep kind of thing where we're doing an experiment multiple times and seeing what happens with different values. So that's a list. And a list also is fundamentally ordered. Sometimes, though, things aren't ordered. Maybe there's no inherent reason that the soma should come before or after the axon, or the axon before or after the apical. So if I wanted to have a list of parts of a collection of parts of the cell and their diameters, I wouldn't, it's not necessarily natural to impose a specific order on that. So we use what's known as a dictionary. And in a dictionary, we specify our own key value mappings. So the values, the diameters are 10 microns, 2 microns, and 5 microns. But there's no reason that the soma should be first or the axon should be second. So I'll just say, oh, hey, the soma's diameter is 10, the axon's diameter is 2, the apical's 5. But it would work the same. All of my code would be exactly the same later if I were to put them in a different order, because I'm assigning my own names to things. So if I have diameters is the dictionary that maps, anytime you say soma, it says 10. You say axon, it says 2. You say apical, it says 5. So then I can grab the apical value from diameters, and it's going to be 5. Or the soma value from the diameters, and it's going to be 10. We can, however, loop over everything if we have a collection of stuff, dictionary, and we want to get both the keys and the values. We can loop over them using this sort of a syntax. So it's for whatever the key is, whatever the value is in our dictionary dot items. So we have the soma is 10, the apical's 2, the axon's 5. So the first time through, name is going to be soma, diameter is going to be 10. The next time through, name is going to be axon, diameter is going to be 2, and so forth. And then so we'll just print that out accordingly. The diameter of the soma is 10 microns. The diameter of the axon is 2 microns. The diameter of the apical is 5 microns. It's often convenient. So here I'm using print, by the way, as to sort of concatenate a bunch of things. Like I'm printing an exact text, a variable, some more exact text, a variable, some more exact text. We can actually use what's known as an F string or a formatted string to do this. And basically the idea with a formatted string is if I have some variable, let's say t-stop, I want to run my simulation until time t-stop milliseconds. So t-stop is 10, let's say. And I can declare a string. And it's normally, I'd say, just say quotation marks. But if I put that F in front of it, I'm going to do the exact text of everything inside the quotation marks, until and unless I get to this little curly bracket situation. And if I find a curly bracket situation, I will plug in the value in this case, t-stop inside that location. So this turns my string into a string that says we should stop at t equals, and then I grab the value of t-stop, so 10 milliseconds. Let's see what happens when we print it out. Sure enough. Now, after you run it, it is a honest to goodness string. It will not change if t-stop's value changes. You can also do other kinds of fancier things when you're doing these formatting operations. So you can specify the number of digits to display, for example. So here, pi is a number, and I can round it to show it with 5 digits, or I can show it with 7 digits, 7 total digits, or what have you. All right, so we're able to do basic calculations. We're able to loop over things. We're able to display results, numerical results in some reasonable way. That's great. Let's say, though, that we want to do a calculation. We want to do a calculation over and over again. We use what's known as a function. We give things, again, we give things a name. Now we're going to give a name to the entire calculation. So maybe I want to calculate the volume of a cylindrical dendrite, and it's going to have a certain diameter. It's going to have a certain length. Well, the volume of a cylinder has a certain formula, and I can just declare that formula. And then I refer to that, so I gave it the name volume of a cylinder. And so here now I can calculate it over and over again. I'll just pass in the value for the diameter and the value for the length, sort of positional arguments here. And then it runs that calculation. And so the nice thing about this is I've given it a name. Even if I only use it once, it makes it that much more readable, because I can go and I can see, hey, look, this is the volume of a cylinder. I know why that formula was there. So that's helpful. And I can do this again if I actually had a section named apical and it had a diameter and a length, and I knew it to be a straight cylinder, because it doesn't have to be. I could go ahead and do that kind of calculation as well. And finally, and this is where sort of NEURON comes back in, and we've already seen this bit of magic. We can load external libraries, or we can load libraries. So for example, Python has what's known as the math library. If I want to load the math library, I'd say import math. If I wanted to load a library known as pandas, which is actually a thing, I could say import pandas. And then so inside the math library, there are many functions and there are many variables, as I'm sure you could imagine. In particular, there's math.cos for cosine and math.pi. So we can call them math.cos as a function, math.pi as a variable. So sure enough, if I take the math.cosine of pi over 3, it's a half. That sounds familiar. We can also sometimes give things, it's also common often to give things a name. So I will, maybe if I'm using pandas, there's a convention that we just give it a name. We call it PD maybe, because who wants to type pandas all the time? So import pandas as PD just sort of redefines the name of it. And then it would be PD dot whatever. Whereas if I said import pandas, it would be pandas dot whatever. And I can grab individual items from a library. So from sklearn.linear model, I can import logistic regression. sklearn is a library for classic machine learning type problems. So I could do this. For NEURON, obviously we'll want to do from NEURON import H. We've seen that already. From NEURON import GUI enables the graphical interface. If, by the way, that you find yourself running a graphical thing and it's not responding, check to see if you've actually done that import of GUI. Yeah, and there's a ton of Python modules, and I can't begin to do this justice, but things that you'll want to look up are, definitely be interested in things in math. NumPy has some support for vectorized calculations, matrices, that sort of thing. Pandas is the go-to library for sort of data sciencey questions, data frames, database access. I already talked about sklearn, which is part of this, which is the scikit-learn module, which provides machine learning. And there's a ton of graphics libraries. So Plotly, I like because it gives nice interactive graphics within Jupyter notebooks. You can also use Plot9, which is where you get ggplot in Python, or matplotlib, whatever works. And so just as an example, and I don't want to go through all this in great gory detail, so I'll just point out, here's code in this notebook. You can check it out for taking a bunch of t-values and a bunch of data values, in this case, the squares, the t-values, and plotting them nicely using ggplot, or we might want to do the same thing with Plotly. So this is what it looks like if you do it with Plotly. Nice thing with Plotly is if you mouse over it, you get these interactive points. It tells you where things are. You can zoom in and out and such. So one of the other things that I want to throw out there, Python is great because it provides a set of built-in help capabilities. So you can find out, so let's say I've done import pandas as PD, and I want to see, well, what all is in PD? What are the things that I can PD dot? Well, I can do the dir of PD, and then I can see that there's actually a giant list of classes and functions and whatever all inside the pandas module. If I find something that's of interest to me, I can do help on it. And I can say help of go.figure, and that'll tell me what the parameters are. And it's very long, apparently. Okay, that may have been a poor choice of things, but it's very long. So I can get a ton of documentation on any individual thing that I might want to look up, which is very helpful. I can also, Python is extremely widely used. If you want to learn more about any particular Python thing that you find, the official documentation on docs.python.org is generally fabulous. There's also Stack Overflow, which is a general purpose programming forum. And of course, we have the NEURON Python programmers reference. We've got a bunch of tutorials and examples. And of course, there's always the NEURON forum if you should have any NEURON related programming questions. That's a great place to go. So with that, that is the longer than I intended overview of Python itself, but I think it's important to have some sort of a framework for what the language looks like before we talk about how we actually script with it in NEURON. Any questions on anything that we sort of ran through, admittedly rather fast? Okay. If not, let's keep going. So how do we actually use this with NEURON? Well, fundamentally, the core NEURON functionality is available through the H submodule. So you're almost always going to write from NEURON import H. Anytime you try and do anything with NEURON, I strongly encourage you to include units in your code. It just makes everything more readable. It's 5 what? It's 5 millivolts. Oh, okay. If you're used to NEURON, you know what the unit should be. And these are NEURON's default units are typically the units that you want to think in neuroscience. That's by design. But if sometimes you may have a wide range of units. If you're doing anything sort of chemical dynamics, things could be very slow or very low concentrations, and you may want to express things in other units. If you are talking about chemical dynamics, from NEURON import RxD. So there's many, many things inside of the NEURON module, but these are the main ones. Additionally, NEURON provides, so that's Python loading NEURON. NEURON itself provides a set of libraries For example, we've seen there's a library for importing 3D morphologies from SWC or NeuroLucid or eutectic files. We can use h.load file to load neuron libraries, load anything, if you any sort of HOK or whatever session files that you might come across. Load file is the go-to tool for that. And so in particular, you'll often want to load file std_run.HOK, which provides Neuron's standard run system. We've seen the run control. It's what powers that in some levels. So you have, I'm going to run for a certain period of time. I want to, so yeah, so that's extremely useful to be able to have. All right, so we've got Neuron, we've got some libraries. Well, okay, we want to actually do something. And we know that the go-to tool, the fundamental thing in Neuron, everything is built out of sections. So how do we create a section? All right, maybe we've done it in the GUI and we've exported it to a session file and then we've loaded it back in which case, awesome. Maybe we've used the import 3D library, as I showed you on the earlier slides, and then we've imported it in, and that's awesome. Maybe we do want to do it from scratch. So if we did want to do it from scratch, since everything's through H, not surprisingly, we end up saying H dot. And how do we get a section? We say h.Section, and we give it a name. So I'm going to define my section. h.Section has a name of apical. And I'm going to assign that to a variable. And you might think that that's a little duplicative, but it's really not if you think about it, because the name applies to the section. I could easily have many variables that refer to the same object, right? Hey, look, there are many people talking about the soma or the apical dendrite or whatever, but it still only has one, it still only exists once, it only has one name. And this is, if you think about it, you have to do this, you have to have this for for loops. Otherwise, you know, you wouldn't be able to loop over sections if you couldn't have different variables referring to the same object. And you can print out a section name, you can get the string name of it. A section has many properties. A section has a length, a section has a diameter. This is a dangerous one. I'd actually stay away from it because the diameter is, it's not really the right place to ask for diameter, segments, and not even segments. If you're dealing with a 3D shape, you want to get the diameters at each of the measured 3D points. We'll get there if we don't look up diam 3D in the documentation. And a section also has discretization, so I've chopped it into a number of pieces. For various reasons, it's always good to chop it into an odd number of pieces. So I might say dend.nseg is 3 or dend.nseg is 5. Or if I want to do this right, there's what's known as the d lambda rule that you can look up, which provides a principled way for decomposing a section into numerical pieces. If you're working inside of a cell class because you want to give things, have things appear multiple times, you want to define a pyramidal cell and then just have a network of 1,000 pyramidal cells. Well, then we need to identify what cell the section belongs to. And then so in addition to giving it a name of the soma, well, which soma? Well, it's the soma that belongs in the cell self. And self is a Python convention when you're referring to the self object in a class. And if there's questions on that, we can explain later. So fundamentally, so to give you an example of this sort of in practice, if I have a section and I want to loop over, have a section, call it den, I can set the length to be 3 watts. That's why you use units. The length should be 3 microns. The default units are microns. The diameter is 2 microns. The nseg, or number of compartments, is 3. I can loop over my section. Well, what's a section made up? A section is made up of segments. And so for seg and den is going to loop over every segment in my section. And I can print out the segment and the segment area. So den that's centered at 0.166 in the normalized position has a certain area, 2 pi, and so forth for all the others. If I have a segment, I can go back and find the section that the segment belongs to and the position. And I can do all kinds of things with this. Fundamentally, cells are made of the collection of sections. I can connect a section to another using the connect method on a section. I can see the topology of cells and how everything's gone together using h.topology. So for example, if I have this code, which defines a whole bunch of sections, connects them together, and then prints out the topology, I can see that the proximal apical is connected to the end of the soma, and then apic 1 and 2 are connected at the end of that. Proximal basal is connected at the beginning of the soma, right? It's not at the same point as the proximal apical. Why is that? Because I said it's not connected to the soma, it's connected to the soma zero end. And that, by the way, is how we can access an individual segment given a location. And so that gives us this. And I really don't want to belabor this too much. Units are your friend. The one thing that I will warn you about, neurons' default values are based on the Squid giant axon. Why? Because that's what Hodgkin-Huxley used. However, the Squid giant axon turns out was not small. And so the diameter, the default section diameter is 500 microns. The default axial resistivity is 35.4 ohm centimeters. Default temperature assumption, 6.3 degrees Celsius. None of these are likely to be very useful in a mammalian context. So if you're thinking about mammals, you probably need to think about changing these values. I've already sort of mentioned that we should define classes of cells rather than individual cells. Here's code how to do it. Happy to talk offline or afterwards about this in detail, but in the interest of time, I'll largely skip over that. When we do this, we can, once we've done it, here's why we do it though. If I create this thing called a pyramidal cell, I can then go back and define it as a pyramidal cell, and I can make another one just by invoking it. And moreover, I can use what's known as a list comprehension, and I can build a list of 1,000 pyramidal cells in a single line of code. So that's extremely powerful to be able to define, this is what the cell looks like, now give me 1,000 of them. We've seen that you can use a shape plot, or in the code, it is unfortunately called a PlotShape, to look at the pictures. You can do this if you pass true instead of false. Here, it'll launch a interviews windows, which is the same neuron traditional graphics. If you pass false instead, you can use Plotly or Matplotlib to get a Python-based graphics representation of your cell as well. You can specify, hey, look, show me some variable and color coding. So give me a heat map, basically, of the membrane potential across the cell. Range var plot gives you the space plot, how things change along a path. So here, the path of voltage between the zero end of the main section and the one end of the DIN2 section. And we have, again, tutorials on all of these things. We have a naming convention, neuron has a naming convention. If I want to refer to the voltage, it's V. If I want to refer to the sodium that's inside the membrane, it's NAI, or NaO for that, which is just outside. The current is INA. If I need to do a recording, if I want to record how does a current or a concentration change over time, instead of recording on the value itself, which is so seg.nai is the value of sodium right now in the segment. Seg.ref.nai is the concept, in C++, this would be called a pointer. It's the concept of sodium concentration at this time, concept of sodium concentration. So it's going to change over time, or the value that it refers to is going to change over time. And that's what we allow to record. We can pass these to PlotShape and range var plot to make it easy to graph them. If I have, all right, so that's useful for plotting. So here, range var plot was plotted over voltage. If I want to do plot over sodium concentration, be plotting NAI, and so forth. If I have a mechanism, right, that I want to put Hodgkin-Huxley channels there. So in the mod file, it was given a suffix, you may have noticed, of HH. So we refer to Hodgkin-Huxley in neuron with HH, or since it's through neuron, it's actually h.HH. I want to put h.HH, the Hodgkin-Huxley channels. Where do I want to put them? Well, I can insert the Hodgkin-Huxley channels into the apical dendrites, or I can insert them into a list of sections, or maybe I even insert them into all sections. I can actually insert them one at a time the other way, so you'll also find code that instead of saying the mechanism.insert, you'll find the section.insert, and they both work. We've already sort of talked about mod files, so skip over that. We've talked about defining these things. If I have a point process, so we've seen current clamp injection. So if I want to inject a current clamp in neuron, a current clamp is called an I clamp. So I will say an h.I clamp, right? And where is my I clamp going? Well, my I clamp is going to the 0.5 location of the soma. So this is a point process that is a current clamp that is injecting current into the center of the soma. I can always go back and find out where something is and move it if I should so desire later. Parameters are specified using the dot notation. So if I have the apical 0.2, that's the segment of the apical that contains, that's 20% of the way in, that has, let's say, Hodgkin-Huxley channels in it. Don't know why, but it would, let's suppose. Suppose it does have Hodgkin-Huxley channels in there. So I say apical 0.2.hh gives me the Hodgkin-Huxley mechanism in that location. And then I can say .gk bar to get the potassium maximum conductance there. I can read that, I can set it, and so forth. I can set INSEG, the number of compartments, the same way. If I need to specify temperature, because remember temperature is by default 6.3 degrees Celsius, because the squid like it, mammals don't. I can say h.Celsius equals 37. Now, mammals like it, squids don't. Yeah. So there's a lot in the slides. You have them, they're on the GitHub. I'm just going to sort of skip over and give some highlights in the interest of time. If I want to record concentrations or membrane potentials over time and how things change, the instantaneous membrane potential location, so axon 0.5, at the center of the axon, the instantaneous membrane potential is axon 0.5.v. If I want to record how that changes over time, I'll construct a vector. So v is h.vector. It's a vector that's going to record some specific location, let's say on the axon, and then the concept of voltage. So I'm going to record the time varying values of voltage. So it's underbar ref underbar v. If you pass in .v, it'll give you an error. I think it'll even suggest, are you missing an underbar ref? If you see that error, you're probably missing an underbar ref underbar. I also like to always record, in addition to my state variables, always record time, because maybe this way I'm safe if I should go back and decide that I want to change the value of h.dt, the time step, or use variable step integration. This way I'll always know which voltage values correspond to what time values, and I don't have to guess. We can also explicitly record spike times using a netcon. Spike times are good things to know, especially in a network. There's various ways that we might want to stimulate. So we have, fundamentally, we've specified, we have sections, and we've seen import 3D. We have sections, we have ways of specifying morphology. We have density mechanisms like HH that we could insert. We have point processes that we could use to like have a current clamp injection. So how do we actually stimulate our model? Well, we might use a current clamp. And if we want to use a current clamp, this is how we do it. It's specify a delay, a duration, amplitude, and a location. We might want to simulate our model by manually setting the voltage or using a voltage clamp. We can also play a time varying voltage, clamp. So maybe it's not holding it constant, but it's forced to follow a certain potential. And then you want to see, well, how does sodium change if the voltage was stuck this way? Well, we can do that in Neuron. We can also simulate synaptic input using a net stem and then specifying synapses and exponentially decaying synapse or netcon, and then a netcon here for connecting it all together. And again, there's many, many examples on the documentation, and I'm happy to discuss afterwards as well. So we've set everything up, we've done the recording, we've given a stimulus to get it to go. Well, how do we actually run it? Well, before we run it, we need to initialize the simulation. We do that using h.f initialize and specify a default voltage. This is basically the value of, so f initializing the negative 65 millivolts, one, sets the membrane potential to be negative 65 millivolts. Hope that's clear. But two, more interestingly, it makes it such that it's been voltage clamped at negative 65 since time negative infinity. So it's always been voltage clamped at negative 65, which means that it has certain implications for what the other state variables will be. You know, your sodium gating variable won't be arbitrary. It'll be whatever it would be had we been voltage clamped there for a long period of time. And then we can run our simulation until a specific time using the continue run function. If we want to do it just one time step at a time, we can also do that using f-advance. So here's what this ends up looking as like as a whole example. I can load Neuron, load the units, define the units, load the matplotlib graphics library just because. And I pretty much always going to want to load standard run just because it gives me a nice ability to say, go run until a certain time. Going to define my soma as a section. It's got a length, it's got a diameter, and that's going to be 10 microns long. I can insert channels into there. Insert a current clamp. A current clamp starts at time 2 milliseconds, runs for 0.1 milliseconds, and has a certain amplitude in, I believe, nanoamps. I can record time, and I can record the voltage at the center of the soma. Initialize, my simulation's been set at a voltage clamp of negative 65 since time negative infinity, and I'll run it for time 10 milliseconds. And then I can just plot T and V. And so here's what we get. We see that this is quite a very strong amount of current to inject it, but you can also see, hey, look, at time 2 milliseconds, we get a jump up, and then the current switches off and takes a little bit before the ion channels take over and drive and generate the action potential. So even though this is strong, it's still driven by the ion channel activity. We can detect spikes using a netcon.record into a vector. You have the slides, the examples here. We can build, if we have more than one cell, we can build networks out of these neurons. So we define a cell in a class, let's say, and we make these two separate cells, two separate instances. I can put a synapse, so an EXP syn, let's say, on the postsynaptic side. And here's a certain location where the EXP syn is going to live. And I'll make my synapse excitatory because its reversal potential is 0 millivolts, so above rest. And on the presynaptic side, I'll put a netcon object, and the netcon will monitor a certain membrane location. So here, for example, I'll monitor the membrane potential at the center of the soma on the presynaptic side. If the membrane potential there crosses some threshold, I believe 10 millivolts is the default, then I'm going to assume that an action potential has occurred, and I will send that notice to the postsynaptic object. And so then it receives it and it starts processing it, and so forth. And so this is just defining the connection. I define a little bit on the postsynaptic side as to what I do, what kind of kinetics, how does current look basically when I get an input, And on the presynaptic side, I say, well, what do I need to monitor to decide that something's happened, decide that neurotransmitter is going to be released. When I do this, I also specify a synaptic delay and a synaptic wait. Fun fact, unless you're talking about a gap junction, which is done in a slightly different way, in real life, delays are always non-zero. They're always positive. There's always takes some time to go from an event being generated, an action potential occurring, to neurotransmitter being received. Yeah, but you can also do gap junctions and all that jazz. It's just a little different. We do have material that we can point you to if you have questions about that. So now, for example, if I take this and I monitor both of my neurons and record both of their membrane potentials with just the code that I've shown you here, then I see the first neuron's membrane potential has that very characteristic, I'm getting a current clamp and current injection while I'm ramping up directly. When the current injection shuts off, first cell generates an action potential. The second cell, the synapse, however, takes that, sees, hey, look, that cell's firing, and sends it over and causes the second cell to fire as well. And so in this way, we can build up a network of neurons. You have to modify this story ever so slightly using identifiers instead of objects. If you want to do what's known as an MPI simulation so that you can run on like your local HPC environment. But if you're just running locally, this will usually work, usually suffice. And I also, I want to point out a couple more things here. I sort of mentioned about data and how do we store data and how do we represent data, because maybe at the end of the day, you use Neuron, you run your simulation, you've gotten your results, but maybe you just want to open it up in Excel and you want to look at it in Excel, and maybe you want to make your graph in Excel. You've got some values. Well, what do? We can, for example, use the pandas module to do that. So if I import pandas as PD, I'll construct a data frame. So let's say I've got two vectors that I've recorded, a time series vector and a voltage vector. Well, I'll just give each a name. So T is going to have the name T and V is going to have the name V. And so this is going to construct what's known as a data frame. It means exactly what a data frame means in R, if you're familiar with that. And once I have this, I can do to CSV and output it as a CSV file. It's going to end up looking like this. CSV is just comma separated variables. So the first thing before the comma is the time. The second thing after the comma is the voltage. You don't even have to worry about that. If you just file open on a CSV in Excel, it will do the right thing. There's also a to Excel function and some other things. And you can reverse this if you have data. So maybe you have a simulation train. You've done some current injections or voltage clamp experiments with a wet lab, and you've done those experiments and they're actual real experimental data, and you want to feed that into your virtual cell. You can use pd.read CSV to go ahead and read the time series data, and then you can turn this into vectors. So I can read in the time values, I can read in the voltages from my data file. And then I can use this with vector.play to generate time varying current clamp or voltage clamp or what have you. So that's the whirlwind introduction to scripting with Neuron. What I do want to point out, to get us sort of back on track time-wise, inside of the GitHub for this course, we have this folder called Notebooks. Inside of Notebooks, we have a collection of, sorry, give me 1 second. Inside of Notebooks, we have a collection of Jupyter Notebooks. So I can click on one of these things and say infio1.example, for example. And so here we are. I can install Neuron if I'm running locally. I did this in Google Colab. I can load my libraries, and here I find this is an example of using what's known as an integrated fire cell. And it's going to have a certain time constant, a certain refractory period. And I can build this, I can build a net stem to drive the cell. And I can see, hey, look, I get a whole bunch of excitatory stimuli, and I want to generate some output. And the cell only fires every so often. And there it is. And so I get a raster plot. And so if you want to know how to make a raster plot, that's how you make a raster plot. And so anyways, and likewise, we have a bunch of examples of things that you might be interested in. So current clamp experiments, sort of straightforward current clamp experiments, ramp currents, recording data whenever a spike happens, looking at the shape plot of a shape that you download from Neuromorpho, looking at how do I generate a video. I don't know if this is going to work in GitHub. Let's see. It does not. I'd have to. Let's see. So out of the generating the video. So let's see. So at the end of that one, you know, this was all done in Google Colab. Here we are. So I have a dentate gyrus granule cell with some rather non-physiological model, but in any case, I can build a video and I can go back and look and see how it was that it fires over time. I can share this video. It's literally an MP4. I can download it and do whatever I want with it, post it on YouTube. So the point being, there's tons and tons of Jupyter notebooks that are there. Well, tons. There's, I don't know, 3, 4, 5, 6, 8 Jupyter notebooks that are there that give you some examples. They're not all available otherwise on the Read the Docs, so some of these were put together for this. So yeah, you can go and you can look at them and you can explore how it is to do neuron simulations. So I know that this has been a bit of a whirlwind introduction, but we do have other things going on. So with that, I will stop here and see if anybody has any questions on Python scripting. Again, it's going to take some time of actually doing it, but you have a bunch of examples now in those notebooks. If not, let's go ahead and take the afternoon coffee break and come back at the top of the hour. So 7 minutes.